Thanks for all of you for being here, and thanks to the organizers for allowing me to present my work here. This is something that I've done very recently, actually last month, with Mark Mazet at Oxford, Alexei Malekin, and Marta Buka, a student who might be applying sometime. Yeah, you heard perhaps the name drop Schwinger-Keldysh a couple of times yesterday. I'm going to build up a little bit more on that. Essentially, I'm going to discuss, so we discussed like Schwinger-Keldysh yesterday. It was introduced as an effective field theory framework or an effective action framework for hydrodynamics. My goal today, more or less, just to give you a gist of if you want to skip to the end, to derive these theories for a very particular class of systems, which will be the SYK models. But all right, let me start a bit slow. Good. So I don't know how many of you would identify as a field theorist. I do. And effective field theories are amazing. They allow us to describe, let me put a case that allows us to describe very complicated systems with simple models. So essentially, you have a very complicated system, gazillion number of particles interacting very complicatedly with each other, and you want to sort of forget about all that messy details and extract out some useful information. And effective field theories are great for that. They allow you to develop models based purely on symmetries and some conserved quantities that you might be interested in, some low energy variables that you might be interested in, and then you just go ahead and describe those. Now, as they stand, the normal effective field theory that comes to mind, like writing down an action, doing a variational principle, doing maybe loop diagrams and things, that the vanilla framework only really applies in one of two cases. It either applies at zero temperature. This will be your QCD, QED, standard model even. So these are like field theories where you're talking about correlation functions around the vacuum state, or they apply in thermal equilibrium. So doing equilibrium properties, but at finite temperature. So this will be like your vanilla Landau-Ginzburg model, or something like many effective field theories in condensed matter physics would fall under this class. But if you wanted to do anything other than that, like work not around the vacuum state, do something more complicated, or go like, or in thermal equilibrium, go study time-dependent phenomena, then effective field theories, at least in their vanilla way, stop being useful. And what actually replaces that is what we understand as hydrodynamics. So it's a very field theorist undertaking on what hydrodynamics means. It's essentially a framework which allows you to describe many body systems but operating close to thermal equilibrium in what we say local thermal equilibrium, which means that they are like fluid particles, like you can divide them into individual cells, and each cell is almost as if it is in thermal equilibrium within itself. Now, hydrodynamics is almost like effective field theory. I mean, in the literal sense of the word, it has some local fields which vary over space and time, and whose dynamics you prescribe through some symmetry principles. So as far as that goes, it is already an effective field theory, but it is not really a field theory in the Wilsonian sense of the word, by which I mean that it does not generically ascribe to an effective action. When you discuss hydrodynamics, it's not popping up in your head that you're going to write down an action and then derive equations of motion and so on. But this particular aspect of hydrodynamics has changed recently, which has allowed me to do this work and many others. All right, so the overall idea is that hydrodynamics is very universal. It should apply to almost all systems. Almost comes with a fine print, which I'm not going to say. Almost all of you probably would know that. You have to be relatively close to thermal equilibrium. You have to have a strongly interacting system. It should not be an integrable system, have finite number of conserved quantities. All that things aside, it can be seen almost everywhere around us. And the core idea is that you take some very complicated system with enough interactions and things, and then you would expect that if you let it rest for a long time and look at very large scale observables, almost everything that is complicated will die out, and only excitations that have some reason to be present will be present. And that reason is generally symmetries. So if there's an excitation that cannot decay because of symmetries, it will be like conserved quantities, energy, momenta, charge, particle number, etc. Or there will be some Goldstone modes of spontaneously broken symmetries. So we heard yesterday about U1 modes. There are also phonons that are associated with spontaneously broken translations and so on. And these, other than these two classes, almost everything else decays out at large enough time scales and space scales. And this is precisely what is captured by hydrodynamics. Hydrodynamics prescribes sort of a principle to determine the dynamics of these classes of quantities using symmetries. Almost everybody should be with me at this point. Good. So this was my vanilla sort of the most basic model of hydrodynamics I'm going to talk about today. The simplest thing possible. You take energy, you take a system in which energy is conserved, and if that is so, it will satisfy a continuity equation of that form. So the rate of change of energy will be given by the divergence of some flux. Of course, this is the most basic model of hydrodynamics you can imagine. You can also do conserved momenta, conserved particle numbers, put other kind of symmetries in the game. A lot can be done, but this is the most basic form in which hydrodynamics appears. And the idea is that if you take this flux and you prescribe for me how this flux depends on density locally at every space-time point, then I can tell you using this equation that if you give me the energy density at some particular instance in time, I should be able to evolve that equation to tell energy at any time. That's all what hydrodynamics is in a very zest. So these things are known as constitutive relations. So in this particular case, J is a vector. So you can try to expand it, like try to write down every possible thing that you can write down. And the first leading term appears here is known as a diffusion term. Kappa here is a thermal conductivity. It depends on temperature, and then there's a gradient of temperature. Of course, you need to give me two pieces of data for this to be complete. You need to tell me what is this thermal conductivity as a function of temperature, and second, what is temperature itself as a function of energy. So this here is known as a transport coefficient that you need to tell me, and this here it will be given by the equation of state of the fluid. So you will tell me how temperature depends on energy. It's part of the thermodynamic data that you have to describe. And then there's a thermal conductivity. And of course, you give me this, and then I can go on, plug it into this equation, and pops out the energy diffusion equation, where D is somewhere related to this kappa and the energy. Right. Of course, there are nonlinear corrections, there are higher derivative corrections. You can make your life as complicated as you want, but this is the most basic form in which hydrodynamics would appear. Right. Now I want to sort of emphasize that there's a word deterministic here, by which I mean that there is no ambiguity here. It's a classical system. You give me initial conditions and I should be able to exactly tell you, provided that the code is solvable and other numerical errors and all that things, but I should be able to exactly tell you how energy behaves at a later time. Unfortunately, life is not so kind to us. It is generally known that when you are at finite temperature, there are thermal fluctuations. I mean, the state is not exactly described. It is an ensemble of states given depending on what ensemble you're working in. And there's generally a theorem in thermal field theory. You might have heard of it in many different incarnations. It's known as the fluctuation dissipation theorem. In some sense, what it is telling you is that on the left-hand side, I have, philosophically speaking, the variance of the variable that I'm interested in. If I take this t to be 0, it will be literally the variance. If t is non-zero, this is generally known as a symmetric correlation function. But essentially, this object captures that the average of products is known as not the same as the product of averages. This is what we mean when we say that something is stochastic or something is probabilistic. On the right-hand side, there's this response function. This was also talked about by Peter 2 days ago. Essentially, this captures how the energy density responds to an external perturbation of temperature and things like that. And this is the first coefficient that appears here. There's a whole slew of higher nonlinear response functions that you can have. In some sense, this object knows about dissipation. This object knows about fluctuations. And the theorem tells you that if you have dissipation in your system, you must necessarily have fluctuations. There's no getting out of it. There's an H bar that sits out there. So you might think that's a very quantum phenomena. It's actually not. In the limit t goes to 0, of course, the cot hyperbolic goes to 1. So this is indeed quantum. But if t is non-zero, then essentially you can expand this in high temperature limit. And essentially you will find that there's a leading term that does not vanish, even in the quantum limit. This is essentially telling you that even fluctuations exist even in classical systems, in which, of course, all of us know, they are precisely thermal fluctuations. And the takeaway that I want to take from here is that any self-consistent theory of dissipative hydrodynamics must include fluctuations. Now, I'm not dissing people who don't do stochastic hydrodynamics. Of course, you can make a case for when fluctuations are not important in large N, in large systems, and so on. But just as a consistency principle, you should always include fluctuations in a self-consistent theory of hydrodynamics, is what I'm trying to say. right? Now, you might think this is a very academic curiosity. Of course, you can put in fluctuations and whatnot. What does it give me? And I can make a case for just one thing that it does give me. These are known as long time tails. They were observed in molecular numerical simulations in the 1970s. Since then, people understand them quite well. And the picture one should have in mind is that there are these long range fluctuations that are going to go over long space and time scales. But then there's this microscopic tiny things that are ignored, those high energy fluctuations. Now, while they are not really dynamical in their own right at large distances, what you can have is that they can interact with this and sort of perturb this long time dynamics of this hydrodynamic mode a little bit. And all of that amounts to taking the response function that I talked about in the previous slide. This part here is the classical response function. Many of you might recognize it. It has a strength given by thermal conductivity and a pole given by the diffusion pole. If you were to go back to time domain, this will tell you that time fluctuations, when you do a perturbation, decay exponentially with the exponent given by dk squared. But now you find that because of this, all these complicated effects, there comes a blue term. The blue term is complicated, but the only complication that I want you to emphasize is that there's a d over 2 here. So for instance, in the equal to 3 spatial dimensions, this guy will contain a square root. And a square root means that this is non-analytic. So, and if you know a bit of complex analysis, non-analytic functions give 2 branch cuts in the complex omega plane. So when you do the Fourier transform, you get something more complicated than just exponential. And this leads to a decay that is polynomial or mixes polynomial with exponential and is not exactly exponential at late times. There's a very strong prediction of stochastic hydrodynamics that does not appear in any theory of classical hydro and cannot appear in principle. Right? Good. That was just an aside. I'm not actually going to talk about long time tails. What I'm going to talk about is that how can you incorporate such effects? And the most, like going back to the 1970s, the easiest way to do this is to start again with your energy conservation equation and acknowledge your ignorance about microscopic things. And by what I mean is that you sort of say that, okay, you know that J, which was the constitutive relations, but you also ignore, like put in a small theta term there. A new vector, you should think of it as some microscopic contribution to flux that you did not actually account for in the classical theory. And then all I'm going to do is the most boring thing ever. I'm going to, whenever I compute any observable, I'm going to just average it over this noise theta with some weight W. Right. So essentially saying that I'm going to perform my experiment over many realizations of theta, and then just going to average over theta. Of course, what this weight is has to be a physical input in addition to my classical hydro. In the simplest case, this will just be a Gaussian with some strength. And that strength is actually fixed by fluctuation distribution theorem that we talked about. Right. But once you do this, you can do some formal analysis. You can essentially, here you're supposed to compute these objects on the solutions of the equations of motion. So you introduce a Lagrange multiplier, you integrate out this noise, and essentially after all of that is said and done, you end up with an action. And this action is an effective action in its own right. You can think of it as an effective field theory. Take this action, compute its equations of motion. If you compute the equations of motion associated with chi, you will find that actually there's a linear term in chi here, which will exactly impose the energy conservation equation. In addition, you have some noise piece, and this is the right theory that will give rise to long time tails and also classical hydro in the classical. Yes.
So seeing Martin Seja-Rose makes me think, can you get this theta term from some sort of decoupling of some quartic term in your effective field theory?
Yeah, and so generally this theta is supposed to parameterize everything that is not classical about the theory. So yes, quartic terms, or maybe you have a heavy particle in your theory that you sort of integrated out and it still has some manifestation. So like almost everything that you will have there.
Just to see why you chose this particular type of noise.
I mean, okay, so this kind of noise is known as conservative noise in the sense that I am introducing a noise which is gradient of something in the conservation equation. I could have just introduced like just a scalar term on the right-hand side, which will also work well. Here, I'm assuming that the noise does not violate energy conservation. So I need a noise that still respects the conservation equation. That is why I have a conservative. Yeah.
Yeah. Does the noise term have to be perturbatively small with respect to the non-random case? Or?
I don't know what that means. So it's not perturbatively. I mean, it's small in the sense. Okay, I mean, it's whatever it is, and the strength of the noise is captured by kappa. So essentially, it will be large. I mean, you can sort of do some rescaling. You rescale theta by square root kappa, so that the strength of the noise becomes 1, and then kappa, square root kappa will show up there. So in general, the strength of the noise is controlled by thermal conductivity. So more dissipative your system is, the more strongly it will interact with noise.
Right. So let me rephrase the question.
Yeah.
Okay. So the noise can be as large as we wish. There's no assumption related to the ratio between the J part and the theta part.
And not right now. The assumption will come in when you start doing actually computing something, because you have to account for the fact, okay, all this happens, but you have to compute this average. And this average you cannot always compute. Or in field theory language, there are interactions. And like you cannot do a non-perturbative calculation, you have to do some sort of perturbative analysis. And at that point, you'll have to assume that the contribution from this term is relatively small.
I see. Thank you.
Okay, good. So a couple of things I want you to notice about this action. First, it has no term that is independent of chi-A. So if you sort of ignore the higher nonlinear terms in chi, this acts as a Lagrange multiplier for energy conservation, very important. So the linear terms in chi always act as a Lagrange multiplier for equations of motion. The quadratic term is imaginary. There's an I there, which generally doesn't happen in normal effective field theories. The reactions are perfectly unitary. These are still unitary in some roundabout way, but they're not manifestly unitary, which means that the action can actually have an imaginary part. Also, the coefficient of this term is same as the coefficient of this term, which is also quite important. This is the incarnation of fluctuation dissipation theorem in this effective field theory language, which tells you that some coefficient of the imaginary term, which I will call noise, is related to some coefficient of the dissipative term, kappa. That's up here. Right. So, all right. But here, in this assumption, in this derivation, I assume that this is a very simple form of noise. And if that is true, you can actually go through all the steps and you can derive these yourselves. In general, this will not be true. There's no reason for a noise to be just Gaussian. It can be some very complicated thing. If it's a very complicated thing, you might not even be able to manifestly integrate out theta that I did in the previous slide. But all that things aside, you can at least expect that if you had done all of those things formally, you would end up with an Lagrangian or effective Lagrangian that looks something like this. As I said, the linear term will always be proportional to equations of motion of your theory. So that part is done. That is completely fixed by classical hydrodynamics. Then there are pieces that will be constrained by fluctuation dissipation theorem. In the previous slide, I had a quadratic piece that had the same coefficient kappa as the dissipative term. So that was fixed by fluctuation dissipation theorem. But then there'll be a whole slew of other things that are not fixed by fluctuation dissipation. So they're like additional information that you have to put in to complete your theory, additional data that you have to prescribe for effective field theory that is not captured by just classical saddle point. And this, in general, are known as Schwinger-Keldysh EFT. So these, so it will reduce to the MSR, the Martin-Segeros EFT that we discussed on the previous slide, in certain regime. In particular, if you only truncate your theory to quadratic order in noise, up to some caveats, and if you look at fluctuations that are much, much smaller than the quantum scale. So there's a quantum scale, which is T over H bar. You remember in fluctuation dissipation theorem, I did an expansion in H bar. And if you sort of work within that regime, then you will find that this effective field theory will actually boil down to what people have been doing for over 50 years. But in general, this will have a more complicated structure. Nonetheless, it will not be manifestly unitary. There will be an imaginary part of the theory, just like in the MSR case, but it will be strongly constrained by unitarity of the microscopic theory. I mean, whatever this complication is, however, this theory might have an imaginary part, but all of this has to boil down to the fact that all of this is coming from a microscopic theory that is perfectly unitary, has a very well-defined Hamiltonian and everything. In that case, there will be some constraints on this guy. And there will be a new symmetry in the theory, is known as a KMS symmetry, which will impose the fluctuation dissipation relations. And in the previous action, I'm not going to bore you with it, but essentially you can test that this is a symmetry of the theory. So this is a Z2 theory, Z2 symmetry, and it imposes fluctuation dissipation relations. Anyway, people have gone crazy with this. So essentially,
Akash, can I ask a question? Hi. Can you
yeah. As soon as I get my bearings, yeah.
could you say again how you define this MFT timescale? It was probably on one of the previous slides in terms of an equation, but I kind of missed it.
No, yeah, I also forgot to comment on it. So essentially, wait, I went too far. Yeah, so this is the time scale here. So it's like
I can't see the pointer on the screen, right?
you cannot see the point, but can you?
I can only see I can only see your mouse. I can't see anything you're pointing yourself physically.
Yeah, and okay. Anyway, I don't think I can see my mouse. But anyway, in the towards the end of the slide, I have this expansion of quad hyperbolic in terms of frequency. So in there's an intrinsic time scale because omega has units of 1 over time. So whatever multiplies it comes with a time scale. So it's h bar over kt is a time scale. And so it's an intrinsic time scale that is set by fluctuation dissipation relations, or rather it's set by temperature and h bar and so on. So I'm essentially saying that to get the MSR theory from the true Schwinger-Keldysh theory, you have to work in a regime where this suppression h bar omega over kt is small.
That's okay, but I thought that on the last slide that you presented, you had these inequalities where partial t was much less than 1 over t MSR, much less than this 1 over temperature timescale. And I was wondering, what was this t MSR that you were discussing? This t MFT, sorry, MFT.
I mean, okay, that is a new ingredient here. So it's some sort of mean field time. So it's not related to the quantum scale. It could be some lattice spacing, some scale that is coming because of lattice spacing and like time between collisions and things like that. Some intrinsic time scale that exists in the theory, which is not necessarily the quantum scale. So essentially in hydrodynamics, we assume that frequencies are small with respect to any scale in the system. So it should be the smallest scale should be smaller than the smallest scale in your theory, the frequencies. So 1 over t will be set by some whatever microscopic scale you might be interested in, corresponding to lattice or like individual particle scales or whatever. And then h bar over kt is the extreme time scale, which is a quantum time scale when everything you will have to take into account quantum fluctuations.
What goes wrong if you invert the last two inequalities? If you let temperature be smaller than this other microscopic timescale?
Yeah, okay. I mean, so this microscopic timescale is actually defined as the smallest timescale or the largest timescale that you would have in your theory. And so essentially, if you exchange it, the TMFT essentially becomes h bar over kt. So, I mean, by definition, the t will be the largest timescale or smallest. So the largest timescale that you have in your theory, which is comes from the microscopics. So h bar over kt is also, I mean, there's no sense in which you can reverse this, I would say. Like essentially, you can take TMFT to be h bar over kt. So you can take it to be set by 1 over temperature. If the scale is even smaller, then I would just I would just remove the middle term.
Just to connect to something that I think I know better, if I just take a Schwarzschild black hole in ADS and compute its effective field theory, temperature is the only scale, so I can easily realize the two inequalities on the left and on the right.
Right.
But I don't think I exactly know what TMFT is supposed to be.
Yeah, that's fine. Like then there may not be any TMFT, or TMFT can be defined to be h bar over kt. So in theories where there is no other scale other than temperature, then TMFT can be defined to be h bar over kt. Or in large M theories, it can be some scaled up version with respect to h bar over kt and so on. But in general, I mean, it doesn't, I mean, I basically just put it there in case you have other timescales in your theory. So there will be h bar over kt. If you have other timescales in your theory, then they will have to sit in between, and omega has to be much, much smaller than any other timescale in the theory. And that's all about it. So it's not, I mean, nothing here requires there to have a separate time scale that is different from each other.
Okay, thanks.
Yeah. All right, good. I think I was done on the slide. Yeah, so people actually started worrying about these things as a Wilsonian action principle for effective for hydrodynamics, and of course, as a byproduct, I've argued that this describes very well the structure of noise or structure of fluctuations in your hydrodynamic systems. There are a lot of things that you can do with it. So actually, I mean, I already argued that once you go beyond quadratic ordering noise, you will start seeing new parameters that you have to put in your theory. They are known as stochastic transport coefficients. You can classify them, you can go crazy with them. This theory, the framework, in particular, the KMS symmetry also provides you with a symmetry-based explanation. I wouldn't say derivation, I did say derivation, but an explanation for why there is a local second law of thermodynamics in these theories. So where does the entropy current come from in this complicated thing? I won't talk about this today, but just to sort of drop it there. We heard yesterday that it can be used for studying real-time dynamics near critical points. Very interesting. It can be used to study quantum chaos, or at least maximal quantum chaos. We heard from Natalia yesterday. And you can go, there are a lot of other applications, and I did not have time to cite them all, but you can find them. Right. I can give you an argument for what these theories are. I can describe for you. The structure is very rich, very mathematical, very nice. But I have given many talks on that. Today I'm going to take a slightly different route. I want to ask if you can derive one of these theories in some simple model. So by which I mean, I want to come up with a macroscopic model where I can actually derive this object straight away, starting from some macroscopic lattice model. So I don't want to prescribe how to write these terms based on symmetries. I want to rather derive one of these. Now, in general, it's a very complicated undertaking. I mean, not just effective field theory for dissipative systems or whatnot. Even the simplest effective field theory, the simplest effective theory of any sense, are very hard to derive, right? I mean, you have to take some complicated microscopic system, integrate, first of all, make a separation between what do you mean by low energy and high energy degrees of freedom, integrate things out, do some sort of RG, and a very complicated undertaking, let alone for dissipative systems. But there are a class of solvable models where you can do this explicitly, and I want to take one of those and actually test for myself. Does that structure hold? Can you actually write down an effective field theory for hydrodynamics starting from some microscopic theory? And there are a lot of, I mean, you can ask me why I'm doing this particular model. There are many other people, I could have chosen, but in this case, I'm going to look at something known as SYK chains. So here are some interacting models, a one-dimensional interacting model, which is simple enough and solvable enough that you can actually derive things.
Okay.
Yeah.
So you would not include holography in this blue box? Is that because of just the large N, or?
I would. I mean, just anything that you can actually compute there. And people have done holographic computations for Schwinger-Keldysh EFTs as well, right? So, I mean, I would. No.
Okay. Yeah.
I'm right now I'm looking for a lattice model where I can sort of try to reproduce this purely from field theory.
Thanks.
I have nothing against holography, of course. Great. So what are these models? So in the simplest way, I mean, there are a lot of gory details that goes into it. I actually won't go through it in interest of time, but also because I don't know many of those gory details myself. So I'll give you the version that I understand best, which is that it's essentially a large N model of Majorana fermions. So you take n variety of Majorana fermions. Each round box here should be understood as one space point. And so at every space point, you would have P of these Majorana fermions. They will be interacting very complicatedly with each other and with some couplings. So essentially you take n Majorana fermions, take P of them, and you make them interact with each other, which will give rise to a coupling. But actually n choose P number of couplings. So a lot of couplings in your theory, very complicated. I'll do the dumbest thing possible. I'll say that, okay, I don't care what these couplings actually are. I'm going to not look at one particular model, but an ensemble of models that I'm going to just average over all couplings that may appear in the theory. So essentially, n fermions, take P of them at every lattice side, let them interact with some random couplings, and then sum over or average over different realizations of the model, drawing these couplings from a Gaussian distribution.
Would you be relaxing unitarity condition then? Like, because
I mean, that is quite important. I want my microscopic theory to be unitary.
but usually when you average over couplings, like doesn't like it creates subtleties with respect.
Yes, someone else will have to answer that for you. I mean, I know there are some factors of I that you can put in the Hamiltonian. I don't know whether averaging over.
But it probably is not an issue for you. Like,
at least we did not find this to be an issue. We found the same unitarity constraints in the effective field theory that I expected from first principles. Yeah, anyway, but if I did just that, just one individual dot, this will be very boring for me because this theory will not have any spatial interactions. So this theory is time independent, but will have a very trivial energy conservation, which is just epsilon dot equals to 0. So I have to do something more complicated. I have to introduce some spatial interactions. So essentially I take a chain of these dots and I then make them interact in some complicated way. Again, there will be more couplings that I'll have to introduce, but I'm going to do the same dumb thing. I'm going to average over couplings once again, and this is the SYK chain. Right? We'll come to the Hamiltonian itself, but actually this model is known to be solvable, not exactly solvable, but solvable at large n and large p. So in the regime where you have a large number of dots interacting at every point and a large number, variety of fermions in the first place. And they're dominated by what is known as the Schwarzian theory. Again, you don't have to worry about what that is. But essentially, what we show is that you take this and you can actually do the quote-unquote renormalization procedure, I mean, with some control, and you can actually derive the Schwinger-Keldysh EFT for energy diffusion. The version of it was the MSR theory I pointed out a few slides ago. What we have works non-perturbatively in derivatives, by which I mean that you can take it arbitrarily high orders in the derivative expansion, and you can write down, in this particular toy model, you can write down the hydro effective field theory as high orders in the derivative expansion as you want. It works non-linearly in noise, no matter how many quadratic, cubic, quartic noise couplings that you want to put in. I mean, at least in this simple example, you know exactly how the hydrodynamic variables are coming out of the microscopic field, which is quite rare to see in theories of this kind. You can explicitly identify what are the low energy symmetries of your theory. In particular, you can derive the KMS symmetry in these models. And of course, there's an emergent second law of thermodynamics. Again, I'm not going to talk about the last one. Okay, after that rather long introduction that took most of my talk, I'm going to just give you a flavor of how you would go about doing such a derivation. Probably going to be the most technical slide of my talk. Essentially, how do you derive theories of this kind? So the observables that you're interested in are these correlation functions, and they're defined as such. So essentially, what you do is you take any two operators or any number of operators that you're interested in, slap it with the thermal density matrix, e to the power minus beta h, with some normalization which I've ignored, and you take a trace over all states in the Hilbert space. And this is how you define correlation functions. And if you do that, you can do some elementary algebra. So here the operators are understood as Heisenberg operators. You can convert them into Schrödinger operators by introducing a time evolution operator in between. And then you can realize that the thermal density matrix itself can be understood as a time evolution operator in imaginary time, because the time evolution is just e to the power iht. And this is just minus beta. You do some this complex analysis tricks, and essentially you pops out the last expression here. What you're doing here is that you're starting at some initial time ti, running the system up to some time t2, inserting the operator b there, running the system up to t final. At that point, you run backwards in time up to time t1, insert the operator a there, run backwards back to the initial time you started with. And after doing this forward and backward evolution in time, you run into the density matrix piece, which essentially means that you run in the imaginary direction in time for time h bar beta, and then you perform a trace. Right? So this is known as a closed time contour or Schwinger-Keldysh contour. And essentially what it is telling you is a prescription for how to compute correlation functions with finite limitation. There's a version of it for an arbitrary density matrix that is not thermal, but we are going to be interested in just that. And a field theorist's way of actually capturing all of this information is through this path integral. So you take whatever correlation function you're interested in, and you put this inside a path integral where you weight it with different exponents for different parts of the contour. So for the forward part of the contour, you weight it with some microscopic part of the action with some psi1. Then, so essentially 1, 2, and E, they are understood as dynamical fields that are living on different branches of the contour. And essentially you can write down a path integral formulation for computing correlation functions. If you've seen this, very well, but essentially this is how you would compute correlation functions in field theory. But very importantly, it actually takes the same action of your theory, which is a microscopic action of the theory, but you take multiple copies of it depending on which branch of the contour you're interested in. Complicated field theory details, but essentially, once you have such an information, you can define what is known as a generating functional, which is the same information as a path integral, but instead of the action, you just introduce a background field phi, which couples to whatever operator you're interested in. And then you can write down a generating functional for the same path integral that you had in the previous slide. And okay, magic. But essentially the point is that here you are integrating over these psi1, psi2, psi-e, which are essentially fields that are living on the forward, backward, and Euclidean part of the contour. And you say, formally at least, that you do some sort of real-time RG, by which I mean that you do some sort of split of degrees of freedom between UV and IR degrees of freedom. And you would hope that if you can do this procedure with some control, pops out a low energy effective field theory, which is now, again, the object is the same partition function that you're computing, but now you're integrating only over low energy degrees of freedom, and you're weighting with some complicated action that is a function of your degrees of freedom and your variables. Right, now, all the gory details, of course, goes in this step, but whatever that step is, this is the action or the MSR action or the action that I'm actually interested in, the Schwinger-Keldysh effective field theory. In general, this action, even if you started with this kind of expansion of your theory where you could separate one copy of field from the two copy of field, you can sort of separate degrees of freedom that are living on individual parts of the contour. You do this complicated thing, there is no guarantee this will continue to happen. In fact, there's a part of the action where this factorization happens, where degrees of freedom on one part of the contour are separate from the other part of the contour, which precisely corresponds to equilibrium field theories. Then there's a dissipative part, which is also known as influence functional in non-equilibrium field theory, which sort of couples the degrees of freedom on different parts of the contour. Out of those influence functional part, you can have a part that is actually real, and then there's a part that is imaginary. The real part is understood as dissipation, and the imaginary part is understood as fluctuations. These are exactly the three ingredients that I had in the very beginning in when I was doing this MSR kind of path integral. All right. I said that the theory should have some unitarity constraints because the imaginary part cannot be arbitrary. Don't want you to read too much into it, just the fact that there are some constraints that the action must satisfy for the microscopic theory to be unitary. And the theory should have some sort of KMS symmetry. It's a Z2 symmetry, and it turns out the symmetry should act on the background fields that I introduced in my path integral like that. How it is realized on the dynamical fields will depend on the model under consideration. It's like a very normal thing, right? You would know how a symmetry should act on the operators, but the dynamical fields are for you to choose. And depending on how you choose your dynamical fields, the symmetries might act slightly differently on them. And okay. Good. Now, how do I actually do this RG procedure? And the thing that we found useful is that you can start with your microscopic theory, and rather than trying to run the RG in real time, what you do is you first do a Wick rotation. So by which I mean that rather than computing correlation functions on this part, on a contour like this, you compute correlation functions on a contour that just runs in imaginary time, and you do operator insertions in imaginary time. So this is your Euclidean version of the theory. You do Euclidean RG and you end up with a Euclidean version of the effective field theory, which will prescribe for you how to compute expectation values of operators where all the operators are inserted in the imaginary part of the contour. And then you take a leap of faith and you say that, okay, I can take this answer and I can analytically continue it, by which I mean that you do these operator insertions on the imaginary part of the contour, deform the contour a little bit in Lorentzian time by doing some clever analytic continuation tricks, and pops out the answer that you're actually interested in. Some very complicated machinery going in there, but essentially this is just to say that how do you actually do this computation? Yeah.
Why the leap of faith? Like,
I mean, I don't know, many collaborators would not call it, but I don't know whether these two procedures are supposed to commute. Like you're doing first wake rotation, then RG, then analytic continuation. Is it obvious to you that this procedure should give you the same answer as a real-time RG?
no, I missed the RG step. I see.
Yeah.
At least
I mean,
as far
the
as
procedure
analytic,
itself. Sorry, yeah.
for analytic continuation, there are math theorems. So then it depends whether your calculation is powerful enough to obey the conditions on these math theorems that you can do the analytic continuation.
Yeah, so I mean, at least in the simple model that we are actually working with, we are able to do this. My leap of faith part was I don't know whether this procedure will give you the exact same answer if I had started with a microscopic theory and run the real-time RG directly.
Yeah.
There might be some subtleties which I'm going to ignore to do the first step at least. I mean, we have some confidence because we get the answer that we expect, so I would imagine that this works. Anyway, off to the SYK model. These are the gory details that I did not want to point out previously. So this is the normal SYK model where no interactions, no chain and stuff. So essentially at every point, you have this n variety of Majorana fermions, you take p of them and you put them in an interaction term with some couplings. And as I said, you draw these couplings from some random distribution and then you sum over models. It turns out that the Euclidean, at least the Euclidean low energy dynamics of this theory is very well known. In fact, this model is very solvable, specifically in the regime where you take n and p to infinity in this particular order. And if you do that, then the low energy dynamics is governed by the Schwarzian theory. The Euclidean action of the Schwarzian theory is just this, some complicated action. It has very nice properties, which I won't do justification to right now, but essentially it's a theory. The F field here that shows up in the low energy theory is in some sense related to the 2-point function of your fermion fields averaged over all n realizations or over all n fermions. So there's a very interesting story there, but just to say that, take my word for it that this is a low energy description of this Hamiltonian here. Right, good. If you do that, then essentially I've already told you the answer, right? So that's the Euclidean part of the theory. And then all I have to do is this clever analytic continuation, and by which I just essentially take the Euclidean action that I had on the previous slide and essentially slap it on the Schwinger-Keldysh.
Just to clarify,
yes.
So the way that you understand the Schwarzian as coming from the SYK is through Schwinger-Dyson. So it's not by an RG explicitly. It's just going to the low energy.
So if you do this Schwinger-Dyson kind of thing, you get these bilocal fields, right? And after that, you still have to do more work, right? You have to come up with a low energy description.
Right.
Right. So
there's no obvious decoupling. There was no path integral that you do, or you want to see the Schwinger-Dyson as the path integral that implements.
Yeah, I think in the limit, the P goes to infinity, it becomes much simpler. So essentially the Schwinger-Dyson equations are much easier to solve. So then you don't actually need, so there's some things there. So essentially it is still, so it's what you actually end up doing is you're finding the solutions of the Schwinger-Dyson equations, which will give you the saddle on which you have to sit. And then you look at small perturbations around that saddle. So this F field is a low energy perturbation around the saddle. So in that sense, it's a low energy effective field theory around the saddle that is given by the Schwinger.
Yeah, but the way that you have structured your talk, you say, well, there's a point where I need to do RG, but here there was no explicit RG. It was just focusing in
so it's a trick. So essentially my actual calculation that I've done will be only the last part.
There was no cross-graining, there was no degree of freedom, or you want to view the bilocal field as doing that for you. I just want to understand.
I would say so.
Okay.
So Leo, you're right. The way you get the Schwarzian action in these SYK models is that you can write an action in the bilocal fields, and that's still exact. But then there's a kinetic term, there's a derivative of time that you drop. And when you do that, then you find this infrared saddle point. And the fluctuations around that are given by the Schwarzian action. But you're correct that at that point, you've not really done RG, you've neglected a term, cross it off, and then you get the Schwarzian, which is not quite the same as doing everything off shell and solving for the dynamics step by step.
Anyway, okay, but if you trust the regime, at least in some regime of parameters, this is the effective field theory that is describing the Schwarzian, I mean the SYK model to begin with. Then you can do this clever analytic integration step where you take this action and you just weave it on the Schwinger-Keldysh contour and you get something pretty boring. So essentially, this action has precisely the factorization form that I talked previously. It essentially just looks like sum 1 minus sum 2, things on 1 and 2 part of the contour. But granted that you can test that it respects everything that you want it to respect. So in particular, it respects all the 3 unitarity conditions. I will leave it for you to check that they actually hold. And it also respects this weird KMS symmetry. If you look at the KMS symmetry, how it is realized here, it essentially, the first part is just time flip in the first copy of fields, which is of course a symmetry of this action. I mean, okay. If the theory is time reversal invariant, then this is a symmetry of your first part of the theory. And the second one, you're essentially, in addition to doing this time reversal flip, you're doing a translation in time and then a redefinition of the field F itself. And this also turns out to be a symmetry of it. So essentially, this has all the symmetries that you want it to have, but it does not have one crucial ingredient. It does not have any dissipation. And I did not expect it to have any dissipation because it's just over 0 plus 1 dimensional. It has, it does have energy. So essentially, you can take the Schwarzian and you can compute the associated equations of motion associated with this field F, and you find precisely an energy conservation equation where the energy density itself is given by the Schwarzian. So the energy density of the Schwarzian theory is the Schwarzian itself. So I mean, in principle, you get 2 such operators because you have 2 fields, F1 and F2. So essentially, one operator is the energy density operator that lives on the forward part of the contour, another energy density operator that lives on the backward part of the contour. They're not really different. They're just 2 copies of each other. But the associated conservation equation is just epsilon naught equals to 0. I don't get any spatial dynamics. Hey, to get spatial dynamics, I have to do something more. I have to go to the SYK chain, which is an interacting model. So it's essentially the same model as before, where I slap in addition, a space label to every fermion. So this is a plain SYK piece that I had previously, but I have, but essentially I have these couplings which are individually living on each spatial slide. But then in addition, I introduce a nearest neighbor interaction. So I take every pair of these SYK dots and I make them interact with the next one with some couplings which are all angry to again average. Right, some complicated model. But there's Mark Mizet and Marta Buka put out a paper last year. Again, this is not my work, so I'm not going to defend this very well. But people have found this action before as well. So essentially, the low energy dynamics of the theory is given by a generalization of the Schwarzian theory, a spatial generalization of the Schwarzian theory, where the first term again is precisely the Schwarzian theory that we were talking about in the previous slide. But in addition, now you have an interacting term. So it's this term is the term that comes from bilocal interactions. It's some complicated term which introduces 2 time integrals. So the theory in this form is not local in time, it is bilocal in time. And there's an interaction term which you can explicitly write down in terms of fields. Okay. So for the analysis that I am interested in, I will take this as a starting point. I want to take this theory and I want to weave it onto the Schwinger-Keldysh contour to be able to derive my Schwinger-Keldysh EFT at the end. But because this theory is bilocal, I have to be a little bit clever. Because now when I put this theory on the closed time contour, I have to make sure that there are 2 time integrals in the interaction piece, and I take both these times to take different combinations so that I can take both these times to be present on both the parts of the contour. Essentially, the first leg is exactly the same as before. The second leg, you get the first term when both T and T prime actually live on the first part of the contour, so which is why you have these F1 and F1 fields. The second term comes when you take one of the time integrals on the forward contour, another one on the backward contour, and similarly backward, forward, and backward, backward. So there are like 4 different combinations because the theory is bilocal in time. And if you close your eyes, then this should be your Schwinger-Keldysh EFT. I mean, at least in closed form. Only that this is not quite satisfactory. To actually derive the action that I started with, I need something that is local in time. And turns out that the kernel that I had, the bilocality kernel that is present in this theory here, has a sine square, which upon analytic continuation becomes sinh. And this near equilibrium behaves like this. So at least you can, so for time differences, which are much, much larger than the thermal time scale, which I argued is what we are interested in, you can actually take this theory and compute something that is at least approximately local. You can sort of perform this T prime integral, if you will, by doing a perturbative expansion around the saddle point. And if you do that, there's some complicated integrals that you can do, and eventually you can derive your Schwinger-Keldysh EFT. So like the first part here is again exactly the same as a Schwarzian, but then now you will have a coupling part or the influence functional part that will come out of this procedure. Here are the results. So essentially, if you do all this procedure, we get a very complicated mathematical code, which has like many, many lines of effective action. But if you do this truncation to leading order in derivatives, of course, you have to be careful how you define derivative expansion, but modulo all of that pops out the MSR action that I was interested in. But I have
This is an identification of the temperature that you're doing.
Yeah.
Okay. Yeah,
So,
I was.
Yeah. So in the previous slide, up until the previous slide,
Right,
degrees of freedom were F1 and F2.
Yeah.
So now after doing all of that, I get this action where I have identified that the local dynamical temperature is given by the time derivative of the averages of the 2 fields on the forward and backward contour. The chi-A field that I defined previously, the noise partner is given by the difference of these F1 and F2 fields. And there are, as I said, there are 2 parameters or 2 sort of pieces of data that I have to prescribe. One is how energy depends on temperature or how temperature depends on energy. So this is the equation of state that pops out. So energy in the Schwarzian theory is proportional to T square. Then the thermal conductivity is proportional to T. And then different proportionality coefficients are given by parameters of the model that I'm not highlighting. Now this theory, I mean, okay, I've done a derivative truncation here. The full expression was too ugly to hear, but you can write down the full expression. And you can check that the full expression is also infinite under all the symmetries of my theory. So this is what I was interested in. So in particular, it has all the unitarity constraints as well as the KMS symmetry. And as we discussed before, the KMS symmetry relates the strength of some dissipation terms to some noise terms. Good. Once you have that, you can start playing a lot of things with it. So just like I had 2 copies of energy density operator, now I will have 2 copies of energy flux operator in my theory. So in fact, there will be some, 2 energy densities, 2 energy fluxes. You will now have to do some identification, and you say that the averages of energy densities on the forward and backward part of the contour, this is what you would classically call energy in a classical hydrodynamic theory. But then there's also a difference part, which is now non-zero in this complicated theory, which will be related to some sort of quantum noise that is associated with this energy operator. Same thing you can do with flux, but you can also look at what is the actual hydrodynamic theory that we are describing in this case. And the actual hydrodynamic theory that we are describing in this case is the theory of energy diffusion, but derivative corrected. So the energy density is given by, if you recognize this object, this is the discrete second derivative on the lattice. So the actual energy density is just given by the discrete second derivative of energy on the lattice with some proportionality coefficient. But then you can take this and you can expand it order by order in A by assuming that the lattice spacing is much smaller than the scale that you're interested in. Then you get the leading divergence term, and then you get a whole lot of high derivative terms. You can also identify the flux. The non-perturbatively, the flux is given by this object here. If you do a derivative expansion, then you get the normal diffusion piece, and then you get a whole slew of other terms. Yeah, so this is the point being that this is the non-perturbatively, the classical theory that you're describing, and we can write down the non-perturbative action that is associated with Good. In the time that I have, I just want to identify what are the actual symmetries of my model, which is what which is my takeaway from whole of the story. I want to figure out how to actually construct these EFTs, not particularly in the example that I'm interested in, but what lessons can I learn from it. And this theory, it turns out that there are regular symmetries that you may, actually this theory has time and space translation symmetries in both F1 and F2 fields. You can ask what are the associated Noether currents. The associated Noether currents turn out to be pure noise. So the associated Noether currents do not survive in the classical limit. So there are some purely quantum or statistical noise artifact. There's also a difference time translation symmetry where you take F field and you translate it in time oppositely to how you translate F2. So this is like taking time translation on the contour where you move everything on the forward contour forward in time and backward contour backward in time. And this is the actual physical time translation symmetry in your theory, and the associated Noether current turns out to be precisely energy conservation. It also turns out that this particular symmetry is spontaneously broken in your theory. And for people who might know this is known as strong to weak spontaneous symmetry breaking. If you don't know what that is, then don't bother. The theory also has a quote-unquote SL2R symmetry. This is a symmetry of the Schwartzian theory, which survives here as well. It's a spatially local symmetry, so you get a Schwartzian SL2R symmetry at every space-time point. Takes this form. I don't want to go more into it, only that it has 3 generators, and turns out 2 of the generators, which are the non-trivial SL2R generators, are not compatible with derivative expansion. So you don't actually see these symmetries if you truncate the theory at a finite order in derivatives, but there is a shift symmetry in Fs that you do see. And of course, there's a KMS symmetry that I've talked about many times. Yesterday, Natalia was developing or discussing a theory of actual hydrodynamics, where you don't do this sort of microscopic derivation, but rather you try to develop the theory based on symmetry straight away. And this slide is just to say how the 2 pictures match. So in Natalia's picture, she had a fluid spacetime or like a world volume, and then you had 2 copies of these quote-unquote Euler coordinates for every fluid variable that are living on that spacetime. So the degrees of freedom in that prescription for hydrodynamics is essentially you take a fixed spacetime, which is sort of a set of labels, Eulerian labels for every fluid volume, for every fluid world volume. And then at every fluid world volume, there exists 2 Lagrange kind of coordinates, which prescribe what is the actual physical coordinate of your fluid in space, in physical space, but you now take 2 copies of it. And then you can actually, there's some clever manipulation you can do, and essentially you can match 1-to-1 the degrees of freedom that she was talking about yesterday to the degrees of freedom that we have found here in the SYK computation. And in fact, if you look at through the symmetries in a bit detail, it turns out that there are symmetries precisely of this maximal chaos EFT that Natalia was talking yesterday. In fact, the SL2R symmetry, they had 2 additional generators, and those 2 additional generators were the additional shift symmetries that were mentioned yesterday.
Yeah, there's a talk at 11.
Yeah.
In a different one.
So I was anyway at the Outlook, so I'm just gonna skip all of that, and you can talk to me later if you want. And let me just here, which is a summary of what I've talked about, but you can read through it, and thank you very much.
Yes.
Yeah.
This could be a dumb question. Like, what would be like since you're identifying the temperature, what is the meaning of thermalization in this picture? Like, is that a dumb question to ask? Like,
I just don't know how to properly answer that question. So I'm identifying what is a dynamical temperature with theory, so which is separate. I mean, it's like so all of this, if EFT assumes some sort of derivative expansion, at least in the computation. So I'm assuming that locally things don't change too much.
Right.
So which means F fields are also not changing too much. And then I'm identifying what I mean by local temperature, because it's a degree of freedom in my theory. I can choose what definition I want to give it related to these hydroframe transformations. In this picture, I'm giving it the definition that is equal to the other slowly varying fields in my theory. So, but since everything is slowly varying, I would imagine that there is eventually an equilibrium. I mean, there is eventually an equilibrium state where F is just given by some coefficient times time. And in that equilibrium state, that T degree of freedom eventually exactly becomes the global temperature. But all of this is EFT derivative expansion. So T degree of freedom is also varying slowly. And you can ask varying slowly about what, and it would be that thermalization temperature.
Thank you. Very nice talk. Just a curiosity, if instead of Majorana fermions, you had complex fermions, so in which you can define a charge, would you expect the same machinery to apply to an average momentum conservation equation? And
yeah, so if you do just Majorana fermions, the only additional conservation you get is the U1. So in principle, yes, I expect exactly the same thing, but instead of just energy conservation, I mean, so the low energy degree of freedom is not given, low energy theory is not just the Schwarzian, you also get a phase field, which precisely corresponds to the charge carried by like the each fluid volume or whatever. So exactly the same thing should apply, but now I will have two conservation equations side by side, energy. And you can also do more models where this was a lattice model where it does not have any translation symmetry. Like if you have continuous translation symmetry, then you will also get momentum modes and so on. But of course, that the calculation becomes more complicated.
then you have to assume that your couplings are translationally invariant in the first place.
Yeah. Yeah, and so essentially, I mean, you can, there are many generalizations you can do, but each generalization comes with its own complication on top. So it's like one of the simplest things you can do.
All right, I think it's time for coffee, so it's time to get Akash again. And tomorrow night there's a conference dinner. If you want to sign up for that, there's a sheet on the blackboard in the common area.